Hello everyone. Today we will discuss about electric field lines. You have a general idea about the magnetic field lines which you have studied in 10th standard. But here we will first study electric field lines. You are familiar with the concept of electric field. So what are electric field lines? In one way it can be defined as the path followed by a unit positive charge in an electric field if it is free to do so. Right? So this path followed is considered as electric field lines. In other words, electric field lines can be stated as an imaginary path. It may be a straight line or curved path at any point of which the direction of electric field can be found by drawing a tangent at that point. So we'll first mention this. So one way of defining, we'll write down a path along which an isolated unit positive charge will move if free to do so in an external electric field. So this is one way of defining it, or the better definition I would mention it is an imaginary straight or curved path at any point of which the tangent gives the direction of the net electric field at that point. So first thing, this is an imaginary straight or curved path at any point of which the tangent gives the direction of the net electric field at that point. So what does this mean? That if we have a curved path where this charge will move in an external electric field, then at point A, the tangent will give the direction of the electric field at point A. The tangent at this point, if we draw, this will give the direction of the electric field at point B, right? And this concept was given by Faraday. Actually, he had given this concept to find a non-mathematical representation of the electric field. he called it lines of force, which is not accepted nowadays. I'll mention it here only. Which is a misleading term, so we don't use this term. Faraday gave the concept of field lines to give a non-mathematical representation of electric field around charge configurations. But this term electric lines of force is not used these days, because this is a misleading term, especially for magnetism concept. So we use the term electric field lines over here, right? So what are the properties of the field lines? How these give a picture of the representation of the electric field around charge configurations? We'll discuss all this in detail in the present video. So let's consider, suppose we have a charge plus Q over here. We know that electric field is proportional to 1 by r square, and we also know that it is spherically symmetric. That means at fixed distance from this point where this charge is placed, if that distance is kept same, the electric field value will be same. Now, if I want to draw the electric field direction at every point around this charge, I can draw a vector pointing away from this charge, because this is the positive charge, and electric field moves away, points away from the positive charge. So if I am marking this like this, so for this direction the electric field will point this way, for this direction it will move this way, and for this it will be this way. Everywhere, if I am drawing this vector, it is showing the direction of electric field. And as we move away from the charge, the electric field will decrease, because it is inversely proportional to the distance, right? So if we draw these arrows in particular directions such that the size of the arrow represents the magnitude, then we will get arrows like this. So every next time the arrow size will decrease. Similarly here, so if we join all these arrows, we get electric field lines, right? So we can mention it. Size of arrow represents the magnitude of electric field, right? So that means therefore size decreases as we move away. On joining the arrows, we get electric field lines, right? So as you can see here clearly that for a positive plus q charge, if I want to draw the electric field lines, I'll join all these arrows in the same direction. To get the electric field lines, right? So this way we can draw the electric field lines for different configurations, which I'll show here. So this is how we represent it. But for drawing the electric field lines of a positive charge, we will draw these lines. So this will be away from the positive charge. So this is for an isolated positive charge. Then we can draw for isolated negative charge. We know that for a negative charge, the electric field directs towards the negative charge. I could have drawn the arrow here as well. Both are correct. Third, equal and equal positive charges. So equal positive charges means if we have a charge plus q over here and another charge plus q over here at this point, so we know that there will be a force of repulsion, and due to the force of repulsion the lines and these will point away for positive. Similarly, you can see a kind of lateral pressure between the field lines. This shows that there is repulsion, and there is a point where the net electric field due to these two charges is 0, and that point where the net electric field due to these two charges is 0 is called neutral point. So for equal charges the neutral point is at the center of the line joining the two charges. If this point is at A, this point is B, this is at center. So I'll mention it. AN is equal to NB, center, this is the center, so neutral point. What is neutral point? It is a point where net electric field due to these two charges is 0. So this neutral point is at the center for equal positive charges, and in case of equal negative charges also the diagram will be similar. The only thing will be that for negative charge the arrows will point inwards, and neutral point will also remain at the center of the line joining the two charges. So this is pointing towards the negative charge. We will study later that no two field lines can cross each other, because otherwise there will be two tangents at the point of intersection that will show two directions of electric field at a point. So no two electric field lines can cross. So these lines must not cross anywhere. So this you have to keep in your mind while drawing the diagram. So this is also, we know that this is a right. So this was about equal negative charges. Neutral point I have already explained. So I'll have to rub the board before proceeding to the next case. We can take the next case of unequal charges. We are taking positive here only. Negative may we know that the only difference is that the direction of arrows is reverse. If Q1 is greater than Q2 and we have these are the places where these point charges are kept, so we know that the electric field lines will emerge as before. The only difference will be that the neutral point will be closer to the smaller charge. What is a neutral point? Neutral point is the point where the net electric field is 0. So this neutral point will shift towards the less magnitude of charge. Okay, so neutral point that means where E net is 0 is nearer to smaller charge, right? Then we have the case of equal and opposite charges, which is called as dipole. You will study later. Separated by some distance, and this is called as dipole, right? So here we have plus q and we have minus q, equal charges but opposite charges. So we know from positive the electric field lines emerge and at negative these end. So this will be the case. But these will not cross anywhere. And on negative it will terminate. So this is the case. Now this lateral contraction shows attraction between unlike charges. This we have to mention. And in this case the lateral pressure, that means kind of pressure is there. So this lateral pressure shows that there is a repulsion between like charges. Then if we have a positively charged sheet, so this is plus, plus, plus. So we know that electric field lines emerge so at everywhere the electric field lines will be outward. And if it would have been negative, then the arrow would have been in opposite direction towards the inward, towards the negative sheet, right? So, and in case of non-uniform electric field, the electric field lines are not parallel, but in case of uniform electric field, the electric field lines are parallel. So, I'll just mention that also, because we'll be using this concept later. And then I'll draw for non-uniform electric field. For uniform, we have parallel field lines, as we have seen in case of the positively charged sheet. So if these are parallel, this shows and if we have non-uniform, I am showing these field lines for the non-uniform electric field such that the electric field on this side is more. In the next video, we will discuss about the density of field lines, that the density of field lines denotes the intensity. More is the density of field lines, more is the intensity of the electric field over there, which I have mentioned here, right? So this was all about the basic concept of field lines and the electric field lines due to some configurations, fixed configurations. So that's all for now. Have a nice day.